All right, hello everyone. I'm Shelby. I'm the Pod 5 Electrical Director, and I'm going to give you a little breakdown on the Pod 4 architecture as best as I can with this drawing and everything else got up here. Apologize for my voice right off the bat. I lost a fight with a barbell last week, so I'm a little hindered in my speaking abilities. So I'm going to start on the left right here, just a quick little key of what's going on here. Any red solid lines are going to be a high voltage component. Red dashed lines will be a high voltage wire. A blue solid line will be a low voltage component. Blue dotted line will be a low voltage wire, whether it be a signal or a power wire. Any green boxes will be a mechanical system that the electrical system directly interfaces with. The black lines that enclose things are mechanical structures of the pod. A dotted black line will be the controller area network bus, just a networking bus that we use on a couple of our devices. And then a circular dotted black line will be an Ethernet bus that we use to talk between certain modules on the pod. So to start, kind of with the mechanical structure, this big black circle around everything, that is the structure of the pod, just kind of what everything's enclosed in. And then this main box in the middle right here, that is our pressure vessel. Last year we enclosed one component in that was this motor controller, because we were uncertain as to if it could withstand the vacuum environment that the pod operates in. So we played it safe and made a pressurized enclosure for it that it resides in. So the first thing I'll start with, electrically wise, is the high voltage system. You can get more in depth on the system in the high voltage and battery team pages on the wiki page, but this is a good start for now. So the whole high voltage system is powered off of a 295 volt battery pack right here. This battery pack is controlled effectively by a high voltage module right here. The high voltage module controls two basically high voltage and high current rated electric switches called contactors right here and right here. These contactors are switched on and off depending on if the battery should be discharging or not. As far as that goes, what we call the low side contactor is located on pack negative on the battery pack, and that is controlled by our shutdown circuit. This shutdown circuit takes in about 7 inputs of the pod, and if all of them are in a go state, it will close the switch and half of the battery pack will be connected to the motor controller. The other contactor is controlled by what we call the pre-charge circuit. The pre-charge circuit is part of the high voltage powertrain system effectively that interfaces with the motor controller, but the pre-charge circuit just allows a small leakage current to get to the motor controller. So when the high voltage system is flipped on immediately, you won't have a high voltage discrepancy between, say, the contactor right here, where the high voltage differential could create an arc and effectively fuse the contactor shut or cause other damages further along the line. So that's the gist of that right there. Also, as part of this battery pack enclosure, we have a 300 amp fuse that is directly in series with the battery pack. And right connected to that is this guy out here. That is our manual high voltage disconnect. This is used to disconnect the high voltage circuit if both of these electric switches are to fail. It provides a safe way to disarm the high voltage circuit from the outside of the pod without needing to without being able to access the inside of it. So then, once the battery pack is fully engaged, both, like I said, which are controlled by the shutdown circuit and the pre-charge circuit, you have battery pack positive here and battery pack negative here on the Reinhardt motor controller. The motor controller is basically a big power inverter that converts DC current to AC current for our MREX 188 motor. And like I said at the beginning of this video, for Pod 4, we enclosed this in a pressure vessel because we were not 100% sure of the clearances internal to this motor controller, and also the presence of certain electrical components that we were not confident that they would be able to operate in a vacuum environment. Pod 5, we are looking to test this with a little more certainty in a vacuum environment and try and eliminate the motor controller. And again, you can have more detail on these systems, specs, and that kind of thing in the respective system videos. All right, two more parts to the high voltage system that I will add are the Orion battery management system right here and the high voltage indicator circuit. The Orion battery management system directly interfaces with the battery pack to monitor individual cell voltage, current, internal resistance, and temperature to make sure our battery pack is in a solid state of health to discharge and charge for that matter. The Orion battery management system provides a singular signal to the shutdown circuit as one of those inputs to dictate whether or not the battery pack is okay to be discharged or not. The other thing I mentioned is the high voltage indicator circuit. That is a circuit that is directly on pack high and pack low on the battery pack when the contactors are closed, and that will indicate to an indicator light back here that high voltage, there's a complete high voltage circuit present on the pod, mainly for safety reasons, and it is also directly wired to the battery pack, so nothing can go wrong. Say if it was controlled via software and say you lost low voltage power, you would no longer be able to see that light. So we have it directly powered off the battery pack through a pretty beefy step-down converter that plugs it down to 12 volts to power this LED back here. I'll get to those other LEDs later. All right, there are a couple more components on the high voltage system that are actually not at high voltage. They're at low voltage that I just want to run through quick. They are this high voltage system switch, this display back here, and the rest of the enclosure of this, what we call the high voltage module, which controls the high voltage system. So to start with, the high voltage system switch, this is just another input to the shutdown circuit right here. If the switch is open, the shutdown circuit will not be complete and will not be able to power this low side contactor, which will render the battery pack off. The next part that I would like to talk about is the display back here. This display is mainly for aesthetics. It is from one of our sponsors and provides us information from the motor controller and the battery management system that is useful to have offhand, such as the pack voltage, the current pack discharge current, and the current RPM of the motor. It accomplishes this through our CAN bus, our controller area network bus, which is just a networking protocol that these respective devices use. It talks to strictly those two devices to get that information, and then another device on that bus is our single board computer, the BeagleBone, on our high voltage board, or in our high voltage module, and that high voltage board, the BeagleBone on the high voltage module is able to relay those messages to our low voltage module, which I'll get to in a little bit, to send off to the dashboard at the end of the line. All right, there is one more element of the high voltage system that I would like to touch on that I forgot to mention, and that is the installation monitoring device. The installation monitoring device is enclosed or a part of the battery management system. It measures the installation between the high and low voltage systems effectively and lets us know if there is a low resistance path between the two, which would cause a short and ultimately bad things and lots of failures. So that is enclosed in here. There are two places this is used. One is the shutdown circuit again. If this is in a fault state, the shutdown circuit will not power the low side contactor and the battery pack will not be able to discharge. And then it is also used in this light back here. It is simply on if the installation is in a good state, and it is off if the installation is in a fault state. This prevents the case where, say, the light is broken. You still want to be able to approach with safety and check to make sure everything is all right, as opposed to the light being powered on in a fault state, and then if the light goes off, you don't know if it's just off or the light's broken. All right, I will now touch on the low voltage side of things to kind of get that going, the other half of the pod. So the low voltage system is powered off of four batteries, all in parallel right here, that provide 40 amp hours worth of power to the system. So these 4 batteries in parallel go to what we call our battery protection box. This battery protection box protects against an undervoltage situation and also regulates that 12 volts along with boosting it up to 24 volts for some of our solenoids back here. That's what this low voltage dropout, 12 voltage regulator, and 24 volt boost converter are respectively in there. So 2 things just on the power bus of the low voltage system. It is controlled by this low voltage system key, very identical to the high voltage system key, just it controls the low voltage power. And then on the same note, the low voltage light is also on back here if that low voltage power is present. So the low voltage power is then distributed to the 2 modules respectively to power the 3 printed circuit boards that we have in each one. On this pod, we also did break this 12 volts out and the 24 volts out to their respective items that just simply needed power, such as the motor controller, the solenoids, but I left those power lines out of this drawing just to kind of simplify things and keep things clean. So as I was talking about before, we have this high voltage module up here, or we had this high voltage module, and we have a similar looking low voltage module right here, but it serves to control the low voltage systems. So as you might have recall from the high voltage system, the high voltage module talks to the low voltage module via an Ethernet bus. This Ethernet bus is routed to an Ethernet switch, which just breaks out multiple Ethernet connections, which connects to the BeagleBone single board computer on the low voltage module, and it also breaks out to our Rocket radio, which is a radio that broadcasts the information that the BeagleBone dictates it to the dashboard, the external dashboard that the software team overlooks to give us the whole look at the pod and the current state of the pod. Also in this low voltage module are the circuits for our pressure sensors on the pod, our retroreflective sensors, which I'll get to in a second, and our current sense circuits to see how power is being used on the pod. So as I mentioned, the retroreflective sensors back here, they were spaced, there are 3 of them on the shell of the pod this year, and those are our main means of navigation in the tube. There are 3 of them, so we can implement a voting scheme. Basically, if 2 of them see a retroreflective strip on the inside of the tube, then it is pretty safe to say that a strip was there, and we can count that as an increment of distance that the pod has traversed. The pressure sensors that I have listed up here the pressure systems circuits, I should say, go back to these braking trays, which control the braking system based on the current state of the pod. The different elements of the braking system include actuating the solenoid valves that effectively actuate the braking system or not and brake the pod or not, and also the pressure sensors that are part of the braking system, so we can tell if if the tanks have been pressurized correctly, if they are losing pressure, and just if they're in a healthy state overall. So that's the basics of the low voltage system. I'd like to say that the BeagleBones on here are the brains of the pod and effectively what make all this come together. The BeagleBones are single board computers that are programmed by our controls team that implement the state machine based on all these inputs and run the pod through all these different scenarios. If this happens, if this happens, if this fault happens, what's the next step? And always getting to a safe state. So bringing it all together and working with the big ones is the whole control side of things, and I'm sure you can get more information on the controls wiki for that. So that's the basics of the things I have on here. If you guys have any questions, feel free to ask me or any of the other team leads from last year, or any of the past electrical directors. They'll definitely be able to answer it. And yeah, thanks for watching.